Okay, we have seen the activity. Now the next one is regarding the conversion of Celsius to Fahrenheit scale and Fahrenheit to Celsius scale. As you can see here, it's possible to change the Celsius into Fahrenheit, and the formula is simple, 9/5, and the value given in degree Celsius plus 32, and you can find the temperature in degree Fahrenheit. The other one is having the temperature in degree Fahrenheit. It's possible to change into degree Celsius using this simple relation. And the other one, if you want to find in Kelvin form, we have temperature in degree Celsius, you add 273.15, and finally this can easily be changed into Kelvin. Okay, this one is if you want to degree Celsius, you have degree Kelvin, then subtract 273.15, then you'll get degree Celsius from Kelvin. Okay, likewise we have also here, this is just to change degree Fahrenheit into degree Celsius. This one similar to this formula, then adding this 273.15, you'll get degree Kelvin. Okay, the last one is this one, 9/5 degree Kelvin, 273.15, plus there is additional 32, and this one is actually helps us to find in degree Celsius. Remember this formula, degree Celsius, you have temperature degree Kelvin minus 273, so minus 273.15, this one. So these are the formula. Now let's see the second slide. It's all about thermal expansion. So the first one that we see in thermal expansion is linear thermal expansion. So there is also areal expansion, there is also volume expansion. Now let's start from linear expansion. So in the linear expansion, the change in length is directly proportional to the original length, and the change in length is also directly proportional to the change in temperature, which means increasing the length, the original length, you have a large change in the value of change in length, and if the change in temperature is larger, you'll get a large value of change in length. If the change in temperature is smaller, you'll get a smaller value of change in length. So with this, the proportionality constant is called coefficient of linear expansion, and it can be represented by alpha. The coefficient of linear expansion can be represented by alpha. Therefore, it's possible to write change in length is equal to alpha original length multiplied by change in t. Here is the formula. Change in length, alpha original length, change in t. We know that this one is L minus the original length, and if you want to find the final length, which is equal to the original length, so under the brace 1 plus alpha change in t, this one when you substitute is L final minus L initial, so when you this minus L final from the left side to the right side, you'll get this one. L initial is common in both cases, so it becomes 1 plus alpha change in t. Okay, the unit for alpha is simply change in length. If it's given meter, meter cancelled by meter. If it's given centimeter, this one centimeter cancelled by centimeter, and there is a change in temperature, so it is 1/Kelvin or 1/degree Celsius will be the unit in case of linear expansion. Okay, another thing that we have here, different material. So based on this different material, we have a coefficient of linear expansion. So it's given per degree Kelvin. So for example, you can take lead. Lead is 29.29 times 10 raised to minus 6 per Kelvin. Aluminum is 24 times 10 raised to minus 6 per Kelvin. Brass, copper. So whenever you calculate results, so you can take one of these for alpha value, then it's possible to find the final length having the initial length and the change in temperature value. Okay, now let's go to the next slide. It's an example regarding a bimetallic strip which consists of two metals of different coefficient of thermal expansion. One of the metal is A, the other is B. Initially, they have equal lengths. So it will be bent when heated and cooled. So now let's see this one. This is an example. We have A and B. So consider if the coefficient of linear expansion of A is greater than the coefficient of linear expansion of B. Then when it hits this one, or when you increase the temperature of these two material, then this will bend downward this way. It will bend downward. The reason for bending downward is the coefficient of linear expansion of A is larger than B, which means this one expand more than this with equal change in temperature. Okay, if B is greater than A, if the coefficient of linear expansion of B is greater than A, then this one, the red one, expand larger than A, therefore this will bend upward. Yes. Okay, now let's proceed to the next slide. It's about areal expansion. The change in area of solid proportional to initial area, and the change in its temperature, that is change in area, is equal to beta, where beta is equal to 2 times alpha. It's areal expansion. It's not considered in one-dimensional expansion, just linear expansion. So we have beta, so beta times the original area multiplied by the change in temperature, where change in area is directly proportional to the original area, and the change in area also directly proportional to the change in temperature. So change in area is final area minus the initial area. So you can take from the left side to the right side, and the area will be equal to the original area 1 plus beta change in T. Volume expansion. Volume expansion, the change in volume of a solid is proportional to its initial volume and the change in its temperature. So just like the previous one, we have to change this value where gamma is equal to 3 times alpha, where change in V is equal to gamma multiplied by the original volume multiplied by the change in temperature, where change in V is V final minus the V initial. Then you can take from the left side to the right side the V initial. Then V initial and V initial are the same, so we can write outside of this brace. So 1 plus gamma change in T, and gamma is equal to change in V divided by the original over change in T. Okay, so this is what we have regarding linear expansion, areal expansion, and volume expansion. The volume expansion, or some typical coefficient of volume expansion, we have different results like ether, carbon tetrachloride, alcohol, gasoline. All these are written here, which is, for example, for this ether is 1.51 times 10 raised to minus 3. For carbon tetrachloride, it's 1.18 times 10 raised to minus 3. So you can use whenever you solve different equation. Metal A has a coefficient of linear expansion that is 3 times the coefficient of linear expansion of metal B. How does their coefficient of areal expansion beta compare? So whenever you compare their coefficient of linear areal expansion, remember that beta is equal to 2 times alpha. And for A and B, A has coefficient of linear expansion is 3 times. A has 3 times that of B. So if it is 3 times B, therefore for beta, so 1 is 6 because it is 3 times. General, metal A has 6 times alpha value for areal expansion, alpha value of